Your neutrons and protons? Is that what everybody's feeling, or do you have a different idea? I don't hear any objections, so. And that should be the correct answer, right? Yes, so that is correct. So neutrons and protons are contributing to the atomic mass of an atom. Pretty easy, but next one, call again, should be pretty easy, but gotta ask you guys. So the atomic number of an electrically neutral atom is equal to the number of what? Is it the number of electrons, the neutrons, or the protons?
So the number of electrons and protons are equal. Right? These couple of questions, first questions are easy just for you to review. So you okay on this problem? So for this question, both electrons and protons are correct. Yeah. So
The next question for you guys, which is a little bit harder. So an element that has an electron configuration 1s2, 2s2, 2p3 has how many electrons? A little harder than the last one.
Two, 2p.
And take your time to answer. You guys don't have to like say something like right away. Like you guys need to like write it down and like figure it out. Because you can also you guys can like work together to figure it out too. Like this recitations for you guys to learn like questions like this, so that when the exam comes, you guys will be all right.
Yeah, I wish I had figured out to make it easier.
I guess I asked, did you guys review the electron configuration stuff? Right. Yeah, take your time. If you have the answer or if you think you know what it is, raise your hand and we can discuss it. Yeah. Correct. So when you're doing the electron configuration, you got to fill the lowest orbitals first, and then you go up. Yeah.
I gotta remember such a priority.
So we got one answer, which is 7. Did anybody else get anything different? I hear like discussion and stuff, I'm assuming. So I feel like, is anybody still working on it? Do you guys need a little bit more time? We can do like another minute or so, in case anybody else is still trying to work on it, figure it out. We'll go over it a little bit. So far the answer is 7. Let's see if anybody else feels anything different. Is everybody else agreeing with 7? So we got 2 7s, 3 7s, 4 7s, did you? 5 seconds. Is looking like 7. No other numbers?
Is it 7?
I heard another 7, so that we're at like 6 now? Okay, so I think we're overwhelmingly at 7. I think. And yeah, so the answer is for a total of 7. But let's break down why it's 7. Would anybody care to talk about the 1s2, like what that means? Yeah. So I guess another question for you guys: how many electrons can be in the s orbital? That's correct. Yes, I heard 2. And how many can go into the p orbital? For a total of 6. But this element has, what everybody's saying is 7 electrons. So how do we get to 7? I think a little trick to it is actually in the exponent. Definitely practice at home, but I'm noticing if you look at the top there, so we know the s orbital can hold 2 of them. So you have 2 there. The second orbital also has 2 of them. So now you're up to 4. And the p orbital can hold 6, but we only need 3 more. Or there's only 3 more electrons available because of that 3 up there. So you have 7. So again, so both of the 1s and the 2s shells are filled with 2 electrons each for a total of 4. And then you have in the 2p, you have 3 electrons left over, and then that's going to total up to 7. Do you guys have any questions on it, or was it pretty straightforward? I think everybody's okay with that one. Alright, so let's go over to the next one. So for the next question, a little more involved. So which subshells are found in each of the following shells? So you have, definitely give you guys a little more time to figure out this one. So you have electron subshells in the M shell, the L shell, K, and the N shell. You gotta figure out which subshells are found in each of like the main category shell. You guys can work work together to figure it out, and it don't have to be like separated, you know. You guys can work it out together, talk it out. Give you guys like, yeah, maybe like 4 or 5 more minutes.
Wait, is it up here?
Subshells are found in the end shell. In the front. S, P, and D. Anybody have any other guesses that they would like to try? That sounds about right. So the solutions are on the next slide, so we'll confirm everything on the next slide as we discuss it. So then we're saying S, P, and D are in the M shell. So then if we go to B, the K shell, how many electron subshells are in the K shell? Alright, so I'm hearing just S. For part C, how many of the subshells are in the L shell?
Oh, just what the...
So I'm hearing SP. And for the last one, how many subshells for N shell? All of them. So let's. Here it is. Okay, so to discuss a little bit. So yes, the answers that we got from you guys were correct. So let's discuss A a little bit. So I guess a little bit of background too from you guys' slides. So remember, the electrons have wave-like and particle-like characteristics. And 2 wave-like characteristics are electron position in terms of their probability density, and the shape, size, and orientation of the probability density determines what is called the quantum number. So, it did. Okay, so for the M shell, we see the value or the quantum number for the M shell is n is equal to 3. And with n is equal to 3, you have S, P, and D subshells, which are all possible. In the K shell, you only have n is equal to 1, which means you can only have the S subshell. In the L shell, your quantum number is equal to 2, so that means you only have S and P subshells, which are possible. And for the N shell, you have an n equals 4, and like you guys mentioned, you can have all of them, S, P, D, and F. Are there any other questions on this one, or you guys feel good about it? Okay, so now this one's done. Let's move ahead to the next one. Okay, so now the next problem is reading what is the maximum number of electrons that each of the following shells can contain. So you have M shell, K shell, L shell, and the N shell. So how many total can they all hold? It's a nice follow-up question to the last question. So it should be too much to figure out. Does anybody know off the top of their head what A is? have it, or are you still working on it? Yeah, shoot for it. I mean, so the last question I would is kind of a nice follow-up to this one, because if you understand how many electrons, or if you understand the subshells in that last question, it should be a little straightforward to answer this one. Right, so for example, like in the M shell, like what is the maximum that it can hold? Right, just M shell. Yeah. Okay. Oh, yes. N shell, so we're thinking 18 for the N shell. Okay, okay. I think you guys got a good handle on it. Is anybody else still working on it? Any questions on this one? So I think if I go to the next slide, does anybody need a little bit more time on it? We got it. How do you guys feel about this one? Yes. I'm sorry, say again? 8, 2, 8, and 16. I think that's the same answers that I've been hearing from a few of the other people. So, yes, let's go to the next one. So now here's a solution for it, but they don't add it up. So, for the M shell, I believe I heard 18 for the M shell. And that's because, like, from the last question, we know that the M shell can hold S, P, and D. And if you add all that up, we know S holds 2 of them, P can hold 6 of them, and D can hold 10 of them. So you add that up, it's 18. So now if you move over to the K shell, we know that the quantum number for that one is 1, and the only thing, or the only subshell that can go into the K shell is the S subshell. So the total for that one should be 2. Going over to the M shell. So the quantum number for that one is 2. And we know S and P can go in there. So that's just 2 plus 6, which is 8. And for the M shell, we have the quantum number is 4. So which means we have both the SPD and F subshells all in there. So at that point, you're just adding up 2 for the S subshell. You're adding up 6 electrons for the P shell. You're adding up 10 electrons for the D shell, and for the F subshell, you're adding up 14. So 14 plus 10 plus 6 plus 2, which I believe should be 32, if I'm not mistaken. Okay. Any questions on that one? You guys feel comfortable with that one? Again, it's kind of like a follow-up to the last one, but so it's a combination of, you gotta understand your N shells, or you have to understand your subshells and your quantum numbers. You gotta understand how many electrons can go to each of those subshells so that you can get the correct answer to this one. Okay, so let's go ahead and move on to the next question. electrons that occupy the outermost field shell are called what electrons? So easy. So I heard valence. If you want to be really like one answer, this one a little easy. That's in here. They talk about that a little bit. Yeah, because the correct answer should be valence electrons for that one. So I'm not sure about the if the professor meant something about like outer shield or something, but technically it's the outer shell. It's typically not filled. So like you learned from your lectures, the electron configurations are technically not stable, so they can bond with other atoms if the conditions are correct. So a pretty easy one. Oh, we have an attendance sheet. Everybody gets to sign the attendance sheet? Okay. Okay, so next question reads, when all the electrons in an atom occupy the lowest possible energy states, the atom is said to be in its what? Is it the ground state, the ionized state, cold state, or regular state? So I heard ground state. Does anybody have any other guesses for this one? I don't hear any other guesses, so I think everybody's on the same page. So yes. So it is in the ground state. But do we remember, I guess, the definition for the ground state? Like, what is the ground state? In simple terms, I guess, you don't have to like from the textbook. Yeah. So technically, the shell is being occupied. So basically, the ground state is just the electrons are occupying the lowest possible energy state. Like it's talking about. So I kind of like tying back to what we were talking about earlier in the class is when you're trying to figure out the electron configuration, you always have to fill the lowest shells first before you go to the other ones. And so ground state is basically saying, hey, like the ground state is when all the electrons in the atom occupy the lowest possible energy states. So let's go ahead, let's move on to the next one. I think we may have maybe 3 more questions after this one, maybe 2 more. I lost count, I don't remember how many we had in this one. Okay, so for this question, calculate the force of attraction in newtons between a cation with a valence of +2 and an anion with a valence of -3. The sectors of which are separated by a distance of 8.6 nanometers. So this is going into more of like equations in you guys' textbook.
interaction and between about 2 and how does that?
I think, oh yeah, question? Ten to the negative 11 is the correct, I guess, multiplier, but the first one that you got there is too big. Yeah, question? That's pretty close, yeah. So, I think you guys have been working it out, so let's go over the answer. So the answer is, that should be 1.9 times 10 to the negative 11 units. So let's see, so let's try to break it down. So it gives a solution. So if you want to solve for the force of attraction between two ions, you're using, from your text equation, 213 and 214. I was actually trying to find 213 because I was trying to learn more and figure out what that equation was, but the only equation that I found was the force of attraction equation, I believe, in your text. But anyway, so they basically put those two equations together, and you ended up with your force of attraction equation there. And they took the first ion, to be a cation, which has a charge of +2, and the second ion as an anion with a charge of -3. So in the Z1, the absolute value of Z1, they put the +2, and in the Z2, they put the -3. And as we know from what they gave us, we know that the distance, or that specified value is named the R, is the distance that they gave us, which is, I believe it's 8.6 nanometers. So now they converted that though from nanometers to meters, so that way you get rid of the meters so that we end up with newtons. Which I'll say in the future, make sure you guys are very careful with your units. Make sure you guys are using like consistent units throughout your calculations so you don't get a weird number. Let me see if I can do my best to explain where they got 2.31 from. I believe, yeah, 2.31 is a very familiar number.
How did we get the equation? So, can be both way, but like the relation between force and energy, if you take derivative from energy, you get the force. And if you take integral from the force, you get the energy. So we have the formula for the energy. Just go down a little bit. Yeah, here. So that's the formula for the energy between two ions, right? And A is some sort of a constant, plus you have Z1 and Z2, which you have to solve with respect to the problem. But if you take derivative from that equation up there, you take the force, and if you substitute all those constant numbers, the final form of the force equation should be scroll down. Equation 2.5. a different version of TextView.
So those equations.
Yeah. Well, yeah. If you take the take the derivative, you get the equation beside in the slides. That's how we get that equation. Yeah, I have different versions of TextView. This one.
So it's definitely different.
So, it's talking about instead of attraction force, it's talking about attraction energy, which we just talked about. So, yeah, this is pretty similar. It's a slightly different form of equation. Yeah, that's the equation just side. So again, just you have the charges +2 and -2, which goes to Z1 and Z2. And yeah. And also you have the R, which here is 3.7 nanometers. Yeah, that's what R represents. Well, it's showing like the total distance between one nucleus to the other.
Yeah, so wouldn't the radius be half of that?
That's the radius of just one atom, or just one element.
But they're separated by that specific distance.
Yes.
So in this situation, it would be half of that, correct? Half of the 3.7 nanometers.
No. This R here is representing the total distance. So you have to plug in the total distance between those two atoms. Exactly. So if it gives you like the radius of the atoms, you have to add up those to get the total distance. Well, this is the energy, right? The previous question here was about the force. So when you take derivatives, you get the R2.
Yeah, so this one kind of similar to the last one. Like Manny was just mentioning, it's the last one was force of attraction. This one is energy of attraction. So if we look at how I can never find my notes on this PowerPoint. Okay, cool. So they work it out. So you have your Z1, which is they're calling the cation, and then the Z2, which they're calling the anion. And then go ahead, they're plugging those values in. Your R, like we stated, is your 3.7 nanometers. And the other value, so once you plug in your, the E, I believe, is related to electrons. I believe the energy of an electron. Okay. And so the epsilon, you guys know what the epsilon is for? Epsilon naught. That's also an important variable in this equation. So the epsilon is a constant that's derived for this problem that we put in there. And if you solve this problem correctly, you should end up with a negative 2.5 times 10 to the 19 joules. Also, that's another thing too that's important. Make sure you guys include. Well, I think since your exam stuff are online, I don't think you guys have to worry about units. But if you're doing practice and stuff by yourself, it's important to. Units are also important too. That way, you're not just like writing down numbers without like a value to it. And this is the next question. So we want to go over this one with you guys. I believe this is also in your homework. And I believe after this one, we'll probably start touching on the homework so you guys can get that finished over the weekend. So the question is reading, using the figure below, which is just the periodic table. Calculate the percent ionic character of the interatomic bonds for the following materials. So you have, I think CS is cesium, cesium chloride, and cesium bromide. I believe this type of question is also in you guys' homework, but so we're gonna do this thing and then jump into homework so we actually work those problems for you guys before we end for today. For some...
Using
You can see in that second line, that's the equation from your text. So you take the 0.7 from, I want to say that element is cesium, and you take the 3 from the chlorine.
So,
Yep.
in the equation, why did it, for the bottom one, it was 0.7 minus 2.8, but the top one is 3.8 minus
Wait, why is it?
3.7. So they flipped the, CS and the CL.
Wait a sec. Why is it flip?
Yes, that is a good question. My initial answer was, in the first one, I thought they were trying to keep it so that it doesn't give like a negative percentage. But now that I'm seeing the bottom, I'm like, wait, that's kind of weird. Ah, that's also true too. Yes, that's very true. Because you're squaring it, yeah, I missed that in the equation. So yes, so it's a little weird, but you're squaring the total value, so the negative, yeah, the negative goes away. So in that first one, you should end up with 73%, and then in that second one, after you plug in your value, you should end up with about 67%. Okay. And let's see. I'm going to try and move this over to so this is the first question.
Yeah, because it doesn't matter, but it's still weird.
Also with the Wiley Plus, I'm not sure, so like for example, the values that you're seeing here, they may be different for you, but the steps should be the same. So like for example, well, not like in this example, the atomic number, but I don't know, like the isotope in that first line, maybe it's not 0.6%, maybe it's like, I don't know, 0.8. So it may vary, but the steps are the same. You just plug the numbers in correctly to the right step. I'm not sure how many started the homework person, but I guess just looking at it, like, is everybody, how comfortable is everybody with this question? Does it look like scary? Is it like crazy? Yeah.
So you just do the summation of all, and then you multiply the percentage of the atomic weight of the metric.
Right, yeah, so that's correct. So what you have is a type of average atomic weights of the hafnium. There's an equation in you guys' text. It's like A bar.
There is.
There's no equation.
No.
Okay. Yeah. So I'm just doing the average of all of the everything that's there for you guys. And I believe for this one, the average atomic mass for the AMU they should have in this case is 178.485. But yeah, so that's correct. You just take your values there, you basically average them, and then that will give you your average atomic weight of the hafnium. So let's see. It's very hard to see from this angle. It's weird. So I have it. It's like an extended screen. Yeah, so I'm extending to you guys here. So for this next one, which I think also might be a little easy for you guys, but let's see. So it's asking for how many grams are in 1 AMU of the material, and part B is asking mole is taken in units of gram mole. On this basis, how many atoms are there in a pound mole of a substance? So for this problem, to determine the number of grams in 1 AMU of material, you basically have to use the formula AMU per atom, gram per mole. So basically it looks like a conversion. So the number of grams per AMU is simply just 1 mole per 6.022 times 10 to the 23 atoms. And to convert that to grams per AMU, you would multiply that by, in the numerator, 1 gram per mole. in the numerator, and in the denominator you would have 1 AMU per atom. And you should end up with, in this problem, in this case, 1.66 times 10 to the negative 24 grams per AMU for part A. I'm trying to figure out, I think I'm better for you guys to see it instead of me telling you. Projector. Actually, they should. Okay.
Just use that.
Right, and then for part B, since there is, hold on, let me check, make sure. Yeah. Since there is 453.6 grams per pound moles, so 1 pound mole is going to equal 453.6 grams per pound mole, and you multiply that by 6.022 times 10 to the 23 atoms per gram mole, and you should end up with 2.73 times 10 to the 26 atoms per pound mole for part B. So again, it's one of those, it's kind of a, actually no, this one's not a conversion. You're taking that value and multiplying by the 6.022 times 10 to the 23. And the units, because of that multiplication, the units will work itself out to be atoms per pound mole, which is what they're asking for. And the actual answer for that should be, in this case, what I have up here is 2.73 times 10 to the 26. So quickly, okay. I want to make sure I get through all the questions for you guys. Okay. So let's go ahead and step through it. So question 3 is saying to complete the 2 following statements regarding quantum mechanical concepts associated with the Bohr model of the atom and refinements that resulted from the wave mechanical atomic model. So in that first one, the sentence should read, 2 important quantum mechanical concepts associated with the Bohr model of the atom are that electrons are particles moving in discrete orbitals, and electron energy is quantized into shells. And that statement is accurate because in the Bohr's model, everything is discrete as it's described in there. Versus in the quantum model, it's more like the atoms are moving, I guess kind of randomly around the atom. So for part A, in that first one, you should have discrete, and in the second slot there you should have shells. And in part B, the statement is reading 2 important refinements resulting from the wave mechanical atomic model are that the electron position is described in terms of a probability distribution, and the probability distribution is from, I'm not sure you guys are familiar with it or if the professor touched on it in class, but it's based on wave theory, where you have like slits. You have a slit wall and you have like a flat wall, and not that they shot electrons at it, but so electrons are passing through these slits, and way back when they found out that the electrons were not hitting the same spot every time. They're hitting different spots within the slit, which means, so that goes back to kind of what we were talking about a little earlier in class today, was waves, or electrons have a wave-like and a particle-like nature to them. So in that first slot, it should be probability distribution. And for the second slide, I'll read it out. So, and it says, and electron energy is quantized into both shells and subshells. Each electron is characterized by 4 quantum numbers. And we know that from earlier today that there's 4 different quantum numbers. And so quickly I'll go to the next one. And yeah, this one's pretty easy. So the statement is reading relative to electrons and electron states. What does the n quantum number specify? And I think everybody has the hang of it because we did plenty of problems like that today. So the n quantum number is specifying the electron shell. So it's not the specific number of electrons. So I guess you can say the electrons are defined by the shell. Like for example, the S shell can hold 2 of them. P orbital can hold 6 of them, and so on and so forth. So that was number 4. This one again, not too bad. To what group in the periodic table would an element with an atomic number 119 belong to? So I mean, this one you just open up the periodic table and you select the correct answer. And in this case, the correct answer is a group, IA, or group 1. Yeah, so this one, not too bad. This one also doesn't seem bad either. I think most people that have already started the homework are doing well with this. So it's asking you which electron subshell is being filled for the rare earth series of elements on the periodic table. And the correct answer to that one should be 4F. And again, to figure out the electron configuration, you got to figure out what their atomic number is, and then from there you figure out how to fill those subshells. Yes?
It said 5F.
5F?
Yeah.
Well, oh no. Yeah, so for this question, it should be 4F. Unless your question on your end is asking, is not asking about rare earth series, and it's asking about a different set of elements.
Oh, my bad. Mine said at 10. I can't set that up.
No worries.
Act 9. My bad.
No worries.
Yeah, I'm confused for a second. Like, what? Sorry.
Yeah, so this one should be 4F.
My bad.
Go to the next one. Halfway through. Let's see. Okay, I see that you guys had a little bit of trouble with this one, so we're going to try and walk through it. So I'll read it out. So the atomic radii of a divalent cation and a monovalent anion are 0.69 and 0.143 nanometers respectively. So in that first question, they're asking you to calculate the force attraction between these two ions, which we already did a question like that earlier today. At their equilibrium and trionic separation. And then the second problem is reading what is the force of repulsion at the same separation distance. I don't think we necessarily did force repulsion, but that equation should be in your text. I see. So we did in class already the force of attraction, so that should be familiar to you guys. You just use that equation and you plug in your values to figure out the force of attraction in part A, which in this case should be 6.66 times 10 to the negative 10 newtons. And the trick for part B is you have force of attraction and you have force of repulsion. Attraction, I guess you can say in this case, is positive. So if you want to figure out the repulsion, you just get basically put a negative in front of that FA. So it's a equilibrium separation distance. Or at the equilibrium separation distance, the sum of attractive and repulsive forces are equal to 0. So basically, it is pushing away on that cation or anion at 6.66 times 10 to the negative 10, but it's also attracting at that same force as well. So that's the relationship there.
Can you walk through that?
Yes, so for part A, yeah, I'm not sure you guys are remembering that one. I know noticing that they don't have markers up here. I wanted to like use some markers so I can like write it for you guys. But so the force of attraction formula, it should be in your text, but I'll read it out to you. Also, it should be on the slides as well that we're going to give to you guys, so that way you guys can review that. But the force of attraction formula is, in the numerator, you have 2.31 times 10 to the negative 28 newtons meters squared. And you're multiplying that by the absolute value of Z1 and Z2. And Z1 and Z2 is basically the charge on the ion. So basically, if it's a cation with a value of 2, you would just put plus 2 in one of them, and then if the anion is minus 1, you would put a minus 1 in Z2. And then you're dividing that by the, basically the distance between those two ions squared. So that's happening in the denominator. And then from there, you just throw it into the calculator, and then you should get out 6.66 times 10 to the negative 10. So yeah, the slides that we did, it will have that equation. You guys can see that, and then also practice as well at the end. There's some questions that we didn't go over. Is there any other questions on this one? Cool. So that one, not too bad. Fortunately, we went over this a little earlier.
If in the book, I want to like find that in the textbook. How do I do that?
In the text, that's a good question. I wonder what section it's in.
Like I know it's chapter 2, but
Is it 2.14? 2.4? Section 2.5 in the text, right? Yeah.
2.5, yeah, when you hit the textbook, it shows it. When you hit textbooks and media, it shows you what lesson was from.
Oh, let me confirm.
Like, just scroll down and hit textbook and media. But
Oh yeah, too. And in the Wiley Plus, they have like a little thing on the sidebar where you can like Control F and you can type in force of attraction. It should take you straight to it. Also, let me see if I can see it here.
I said textbook and media.
I had the textbook open on my end and I don't know where it went. Let me see. Okay, so yeah, so I think it should be in the primary atomic bond stuff. Yeah, so in 2.6 is where they start talking about attractive energy and repulsive energy. And I think if you just scroll a little bit more, it should tell you, or show you the force of attraction equation. Yeah, maybe, just want to check. This is a video. Okay, so yes. There it is, okay. Yeah, so in your textbook, actually, so example problem 2.2, which is in section 2.6, that's where you'll find the force of attraction equation, which the number for that is 2.14. So if you find that, that equation, that's the equation that you would use for to solve that problem. And again, we'll make sure to post all this stuff up for you guys too, so that way you guys can see like the how it is just as is without numbers plugged into it and stuff. So I see in this example problem they have oh no, but it looks like they derive it actually, which is nice. You can see where it comes from. Yeah, so in 2.14 is within the example, and it shows you like the breakdown of how they calculate or how they derive force of attraction. And that equation is the equation that you use for this. And to recap just very quickly, so for part B, whatever you got for part A, just put a negative on it, and that's the force of repulsion. Okay, so let's go to the next one. 10 minutes left, so let's see. This one doesn't seem too bad. I see it. Yeah, not too bad. Oh, it's another force of attraction problem. So this one's reading the force of attraction between the cation and anion. So they give the force this time, and so they want you to find the distance. And basically, you're just manipulating the force of attraction equation so that you can get R instead of getting subscript A. So basically, how the equation should read, you should have R naught is equal to the square root of 2.31 times 10 to the negative 28 Newton meters squared in the numerator. And then also in the numerator, multiplied to that, you have your ZC, which is just the positive value, I guess you can say, of the cation, and multiplied to that, you have the value of the anion next to it, and that value is divided by Fa. And let me see, am I missing anything? And so, at least for this problem, when you solve it, you should end up with a R naught of 0.189 nanometers. See, so the numbers are different. The solution though is the same, but the numbers in my case, and also here, are different. So basically you calculate the R naught, and then from the R naught, so they want the anion radius. And so to determine the anion radius, it's just R naught minus RC, and RC is the cation distance, I believe. And R naught is your so you're given the cation distance, but you are asked to solve for the anion distance, and they gave you R naught, which is the interatomic distance. So basically, to find the anion, you have to take your distance between the two of them and subtract it from the distance, the RC, the distance from the cation. So again, quick recap. So you just take your force of attraction, you manipulate it so that your R naught is what you're solving for. And then once you solve that, you find that number. To find the radius of the anion, you would just take that R naught that you found and subtract it by the radius of the cation, and then that will give you your answer. Okay, so quickly we'll head to the next one. So that last one, a little tricky. You gotta do an extra step. So for this one, this one's not too bad, so I'll read it out for you guys. So what it should read out as is the bonding with electrostatic attraction between oppositely charged ions is called ionic. And then the next sentence should read the bonding with electron sharing between two adjacent atoms such that each atom assumes a stable electron configuration is called covalent. The third sentence in part A should read the bonding where the positively charged ion cores are shielded from one another and also glued together by the sea of valence electrons is called as they say, a metallic bond. So basically part A is going over, I'm pretty sure there's a slide too in you guys in the PowerPoint from class, is going over ionic, covalent, and metallic bonding. Part B is asking about the Pauli exclusion principle. And so they want you to select all the statements that apply. And the two statements might be different on my end. Let me make sure. So the two statements that should be true are that the first statement being electrons with the same state must have opposite spins. And your second answer for this one should also be electron states can hold no more than 2 electrons, which is both true. So one orbital you can't have. This one is related to this one. It's off my head. So basically, you can't have more than 2 electrons in there, and then the same state must have opposite spins. It's related to a specific slide on there, but my brain's not working right now. Okay. So that one, not too bad. It looks like most people that started homework, they did well on this one. So that's just like from the textbook. This one too also isn't too bad. So what type of bonding would be expected for rubber? And for this one, you guys should have answered covalent bonding with some van der Waals bonding. And that's just because of how you just have to look into how rubber behaves, how it's made up, basically. And so, question 11, last one, not too bad. This one, so this is the other one where it's looking at the percent IC. We did this earlier in class as well. So they want you to calculate the percent IC of the interatomic bond for the intermetallic compound. Let me make sure it's the same. I think it's the same. It looks like titanium and aluminum. Actually, not sure what that compound is. And for part B, they want you, based on part A, it looks like, so based on part A, what type of interatomic bonding would you expect to be found in that compound? So for part A, like how we already solved earlier today, you just use your percent ionic character equation, which is basically telling you how electronegative the ions are with each other. And you would plug in your, I think you're plugging your electronegativities into that equation, and then you have your answer. And for part B, you should end up with a metallic bond. Because the percent ion character is, it should be 0%. Sorry, I should have told you guys what I got for that one, but I was worried that it would be the same value. So technically for this one, you should end up with 0% after you work out the math. And the reason for that is because your percent ionic character is 0, and the intermetallic compound is composed of 2 metals, the bonding is completely metallic. And that checks out with, I'm sure what you guys learned so far in class, when you have 2 metals mixed together, you have like a metal alloy. If it was like titanium and, I don't know, some ceramic or some oxide like silicon, it would be a completely different story. And then very quickly, are we done with time? Okay, like 4 minutes. On this one, not too bad. So the question is reading out, what type of bonding would be expected for each of the following materials? For bonds that could share ionic and covalent character, choose the one that would predominate. Let me double check. Oh, for this one, it's like different? Okay. So I mean, brass, we know that is a metal, so let me double check again what I'm asking for. The type of bonding that is expected. So we know brass is a metal, and for rubber, it should be, yes, covalent with van der Waals bonds as well. And, okay. So 347. Do you guys have any other questions on homework? Is there anything like you guys want me to go over real quick to make sure you guys get it done by tomorrow?